Hey everybody, in this video we are going to determine how equilibrium plays a role in the determination of the pH and concentration of weak and strong or weak acids and weak bases. And so some of that equilibrium stuff that we've already learned is going to be a big factor in determining some of these things. Some of these properties for weak acids and bases. Okay, so if you don't know, you'll have to go back and memorize the strong acids and strong bases. If the acid is a strong acid, or you don't have to do equilibrium with them. Okay? If it is a strong base, you don't have to do equilibrium. This is focused solely on determining what the either what the constant. And so let's make sure we keep that. The constant or the conditions are, right? And so for a weak acid. So I use acids as my kind of examples in these things, but bases work just the same way. Different reaction, but same kind of thing, okay? So here's what we have. We have a general reaction. Let me see if I can get rid of some of this stuff, okay? And so a general reaction is one where we start with HA. And we use A is acid, and H is the proton that is out in front. That is the ionizable proton, okay? And when we have an acid reacts with water, H2O, okay, and that's in equilibrium with H3O plus, and then we will say A minus, okay? So now, let's take a look at what we have in this reaction. We have HA, that's our acid, and what happens is that acid dissociates to give you whatever the counter ion is, okay, whatever the negative ion is for that from the acid. Okay, in this case, we're doing it in general as an A minus. Okay, and then so what you see is kind of a Bronsted acid. So the H has been donated to water. Water has gained the proton, and this is what makes things acidic. Is the presence of the hydronium ion, this guy right here. Okay, and so this sort of reaction is true for all weak acids and weak bases. One of the things that I see students do time and time again is when they're given an equilibrium acid or base reaction where they have to do an acid, determine something about a weak acid or a weak base, they change the reaction. Don't change the reaction. Keep the reaction the same. Okay? So, it's always going to take this form. Okay, so now as we go through, you can see, so that's the same thing. I just kind of moved these two. I switched those. Okay, and so then the equilibrium expression is going to be, okay, it's always going to be this. Okay, and it's, again, products over the reactants. This is the products. This is the reactants. Why don't we include water? Because water is a liquid. We only include those things that are aqueous and gaseous. Okay? Sorry. These things are going, slides are going the wrong direction. Okay. Okay? So, we only include those things that are aqueous or gaseous. Now, what ends up happening here, and I'll change the color, is that instead of a Kc, we have a specialized K, and we call that Ka. Okay, and so that's the acid dissociation constant. Okay, so, or the acid equilibrium constant, you'll hear me call. Okay, because technically it's a dissociation constant, because what's happening is that this guy is splitting up; it's disassociating with the acid. Now, these problems end up being really just an equilibrium problem. And remember, there are two types of equilibrium problems. There are find the conditions or find the constant. And so in this case, we are given the somehow we were given the conditions, and so now we have to find the constant. Okay, so what I'm going to do is I'm going to do this problem, and I'm going to do it on the kind of the next page here, if I can, right? I'm going to do it here, and it's formic acid. Let me get rid of that because we don't need that. Okay, so it's formic acid. Let's see here. H. Make sure that it's the right stuff. Okay. So it's formic acid. Okay. So let's write a reaction, and its pH is 2.38, and the concentration is 0.1. Okay, that's all we need. So formic acid, HCOOH plus water. Oops, if I write these things correctly, plus H2O is in equilibrium with H3O plus COOH, and that's a minus here. Okay, so what we have done is we have, in essence, removed this proton, and then this is our A minus, right? So we removed the H, and it's transferred to here. And so what we have left is the A minus. Okay, now what do we do from here? Okay, I am keeping the reaction completely the same. That's the whole idea. Now, it said the concentration of the formic acid was 0.1 molar. So we're going to do this. So ICE, so this is 0.1 molar here. Okay, great. Now, water is a liquid, and this is a solution, a water-based solution, so we don't need that. Okay. Now, we were also given that the pH equals 2.38. Okay. Well, that is kind of an interesting thing because that doesn't tell us directly what any information. Okay. We're going to have to use that, though. Okay. Now, before we actually start doing the problem, let's look here. So this is, how much of this is present before the reaction starts? 0. How much of this is present before the reaction starts? 0. And so now we need to know which way the reaction shifts, and because there's zeros on the product side, we always shift towards the 0. And so now we fill in our ICE chart using x's. So we're going to use some of this up. So this is going to be minus x. This is going to be plus x and plus x. Okay. Now, so this is going to be 0.1 minus x. This is going to be x, and this is going to be x. But we don't have the constant. So how, if we don't have the constant, the Ka, how are we able to do this? Because we don't have the constant, we don't have the conditions. Well, this is where the pH comes in. Because pH is equal to the negative log of the concentration of hydronium ion. And what is this column right here? It's the concentration of hydronium ion. So we can calculate, using our pH stuff, the concentration of the hydronium ion and then plug it in right here. Because the pH is going to be measured after this has reached equilibrium. And so the pH of this reaction is contingent upon this concentration. At the beginning, it's 0, so there's not going to be any pH, but as soon as it starts ionizing or dissociating, you're going to have some. And eventually it'll reach equilibrium, and so that concentration isn't going to change. So what is the math involved here? Okay, so I'm actually going to do something kind of neat. Okay, one of the things that I think may help you is seeing me plug this in the calculator. So I have put my calculator up there. Okay, and so we're going to do this. 2.38 equals the negative log of the concentration of the hydronium ion. So now we need to get rid of negative log. So the first thing that we can do is fairly straightforward mathematically. So we're going to go minus, we're going to multiply by a negative 1. So now both sides. Negative 2.38 equals log of the concentration of H3O plus. Bless me. Okay. And so now how do we get rid of this log? Okay. Well, if you remember Algebra 2 in high school, the inverse function of log is 10 to the whatever. So whatever we do to one side, we have to do to the other side. And so the 10 to the log of the concentration of hydronium ion, these things cancel right out. Okay? But over here now we have 10 to the minus 2.38 is going to equal the concentration of the hydronium ion. Okay? So how does that look in a calculator? So if you, let me get rid of some of this. Okay, so now what I'm going to do is I'm going to get this, okay? So 10 to the, and then I'm just going to do negative 2.38 in parentheses, and what you get is, okay, that the concentration of the hydronium ion equals 0.0042. Okay, 427 if you want it, or 417 if you wanted to, but that's the concentration of the hydronium ion. Is that the end? No, because we have to come back up here. Now we have an X, right? Because isn't the concentration of hydronium ion our X? So now we can find the end conditions, the equilibrium conditions. So this is, and I still have that value up here, so it's 0.0042. Now that is our X. So what do we put in here? Well, those two values are the same because they're both X, 0.042. And then over here is 0.1 minus 0.0042. And so again, I'm going to put that in my calculator, minus 0.0042. And you'll see that that number doesn't change much, but this ends up being 0.0958. Okay. We done now? No, because guess what we have to do? We have to determine the Ka. So let's do that. The Ka then is, and how do we calculate the Ka? Ka equals the concentration of H3O plus times the concentration of COOH minus all over the concentration of HCOOH. And this is calculated using the equilibrium values. So the equilibrium concentration of this is 0.0042. The equilibrium concentration of that guy is 0.0042. The equilibrium concentration of this guy is calculated, I have it calculated right there, so that's 0.0958. And now we do the math. And so please be careful when you do the math here, but so it's going to look 0.0042 times 0.0042, okay, divided by 0.0958. Okay, so we have a Ka here. Ka equals 1.84 times 10 to the minus 4. Remember, Ka doesn't have units, and so what this does is it shows us how to get Ka, or how to use those equilibrium conditions to determine the equilibrium constant. Okay, And so all the things that we've done up to this point kind of relate to this. I would like to think that there's no new real chemistry in this video except for the reaction that we're kind of interested in. Other than that, the rest of this is kind of stuff that we've already dealt with. So, but that's it for this, and we will continue. I'll definitely post some more of this stuff.